No, I think the academic license is really reasonable. It's like $50 or something. But the commercial license is maybe $1,000, but
That's cheap.
well, it's cheap compared to Abacus, right? But I mean, it's also GMesh is free. I don't know about the sophistication of the algorithms in it, and it's the ability to script it and all that. I don't know about also in GMesh. I'm not sure about its ability to create geometry. So in Qubit, you can create the geometry. It's a little crude. It's not exactly like using Pro-E, you know, but you can do it, and you can also do it with a script. So you know, that's why I like to use it. Okay. So there are some gotchas when we talk about plane elasticity. So let's consider a little beam element. And when I say beam, I mean like Euler-Bernoulli beam. Okay, so a beam, you know, resists rotation. So if we imagine some deformed, the dashed line being the deformed position of the beam, we can define some angle here, we'll call theta, x and y. And this deformation would occur when you apply some moment. This distance is 2a. So this is an Euler beam, and it's a continuous beam. We're talking, you know, so we can go back to, you know, undergraduate solid mechanics. And if we do, then the strains in this beam are minus theta y over 2a So you can see the shear strain is 0. This is under the assumption of Euler beam theory, right, where planar sections remain planar, and it's long and slender essentially, right? So you know, if this was a Timoshenko beam, that wouldn't be true, but anyway, we're talking about an Euler beam here. So now let's imagine we're going to model that beam with a 4-noded quad. Right? So with a 4-noded quad, we use a bilinear interpolation, right? So the sides have to remain linear. In other words, you know, if this was a Q8 or something, then we could possibly have a quadratic interpolation, but we don't have mid-side nodes, so the sides have to remain linear. So if we apply a moment to this element, our deformation is going to look like this. And if we compute the strains, we see that the shear strain is not 0. And this is an artifact of the element formulation, and this is a parasitic shear. So it's an artifact of the element formulation. So if we look at the strain energy, if we look at the elastic strain energy, U, for a beam, that should be equal to we're using our definitions from before. From last time. So the elastic strain energy in the continuum should be equal to the moment times the angle. And the elastic strain energy of the element then would be the same. And the moments here are the same, right? We're applying the same moment to both under plane stress assumption. So C is populated with values that would come from the plane stress assumptions, okay? And if we were to plug all that in and look at the ratio of the angle of the element to the continuum angle, we'd get this. Where the term A over B squared is present due to parasitic shear. I guess, I don't know, did I write what B? Maybe it's obvious, but B is this. So if we take the limit as A over B, so this is the sort of aspect ratio of the element, right? If A over B, if A is B, they're equal to each other, it's a perfect square, right? So if we take the limit as A over B goes to infinity of this thing, we get 0, which implies that this is equal to 0 as A over B. What does that mean? The angle of the element over the angle, well, I mean, first of all, what's the only way this equation can be valid? If the angle of the element is 0, right? I mean, it can't be 0, or this equation's not valid. So it means that the angle of the element is 0, and whereas this is non-zero. What does that mean? There's no deformation. The element locked, right? The mesh locks. Okay, and this is an artifact of the discretization. So it's important to understand and know about these things because, you know, the thing is when we say a mesh locks or a mesh is experiencing locking, we don't necessarily mean that it's immovable, right? It really, we use it in the context of finite element analysis, when we talk about locking, we really mean artificial stiffness, okay, or excess stiffness. And this is one of the reasons that we don't like to use triangles, because triangles are excessively stiff, okay? And they can exhibit this phenomenon, okay? And, you know, again, I'll show you an example in a second where it's very clear the thing is locking, but, you know, in a 1,000,000 degree of freedom simulation, you know, in your reservoir or something, it could be, you know, if you don't really know what, you don't understand the element technology, that's why it's important to take a class like this and other more detailed classes in finite elements so you understand some of these things and you know to be aware of them. Because there's no way that you'd ever know this is going on if you weren't aware that it could happen, right? Because, you know, this could just be going on right in the middle of the mesh and you just never know, and you get all this artificial stiffness.